Okay, let's start with this question. The order of hydrolysis of M by 10 solution of K2O, K2S, K2Se, and K2TE will be. Now you're supposed to identify the order of hydrolysis, and these are salts of weak acid and strong base. So in such case, the hydrolysis H will be equal to root of KH by C, wherein KH will be equal to KW by Ka, because we are having the salt of the weak acids. Therefore, H would be equal to root of Kw by Ka into C. Now, Kw and C are constant. Therefore, the hydrolysis in such cases would be inversely proportional to square root of the dissociation constant of the acids. Now, the acids in consideration are water, hydrogen sulfide, hydrogen selenide, and hydrogen telluride. And the acidic strength of these hydrides of group number 16 increases down the group, hydrogen telluride being the strongest acid. So the acid which is strongest, the hydrolysis would be less or least in the case. Therefore, the hydrolysis order would be 1, 2, 3, and 4. Answer would be option A. Next, ammonia obtained from ammonia obtained from zero point 0.4 gram of an organic substance by Gildan method was absorbed in 30 ml 0.245 molar H2SO4. Excess of acid was neutralized by the addition of 30 ml 0.2 molar NaOH. Calculate the percent of nitrogen in the substance. So, as per Gildan's method, we have to use the formula. We have to use the formula to calculate the percent of nitrogen as 1.4 times milli equivalent of the acid upon weight of the organic sample. But the milliequivalent of the acid would be the acid which is actually utilized in the Geldar's method. Now they are saying excess of acid was neutralized by some amount of the base. So how much amount of acid was neutralized, that we can find out by using NaVa for the acid equal to NbVb, meaning equating the equivalence of the acid and the base. Now the acid normality would be molarity into N factor 0.25 into 2. The volume of the acid we are supposed to find. Base के लिए 0.2 molarity N factor 1 NaOH है and 30. So this will be 0.5, and we have the volume of the acid as 2 into 30 divided by 5. That's 12 ml. It means that out of 30 ml, 12 ml is excess, and that is why the 18 ml would be consumed. Therefore, now we can use percent nitrogen in Jelladal's method, which will be equal to 1.4 times. Milli equivalent would be molarity into N factor into the volume in ml, which is 30 minus 12, so into 18 divided by the weight of the organic sample is 0.4 gram given. When you do the calculation, you'll get 31.5% as the answer, which is option A. Which compound does not react with glucose? A question from biomolecules. And in case of glucose, with respect to its open chain structure, it was able to react with HI, undergoing reduction to give N-hexane. It was also able to react with hydroxylamine to give oximes, with hydrogen cyanide to give glucosynohydrine, with bromine water, which is a mild oxidizing agent, to give gluconic acid, with dilute nitric acid giving glucaric or saccharic, a dicarboxylic acid, and also with acetic anhydride to give glucose pentaacetate. So these were the reaction which confirms the open chain structure of glucose. But there were many reactions which we expect with respect to glucose, aldehydic, and the hydroxy functional group, but they failed so. And what were the reactions which failed? Glucose did not show any reaction with sodium bisulfide, ammonia, Schiff's reagent. Also, the glucose pentaacetate, which is the product with acetic anhydride, that was not able to react with a hydroxyl amine. The glucose pentaacetate, it does have the aldehydic group, so it should have a reaction with H2NOH, but it did not react with H2NOH. And we know that the problems with respect to the open chain structure was the open chain structure had only negligible proportion amount when the glucose is dissolved in alcohol or aqueous solution. And the major proportion of glucose exists in the alpha and beta cyclic forms, which are called alpha D plus and beta D plus glucopyranose. So glucose as the open chain structure does not react with ammonia as well as NaHSO3. That's why the answer is both B and C. Next, if the following salts have the same magnitude of the solubility product KSP, same KSP, then the most soluble salt in water is. Now, if you have the same solubility product for most of the salt, then what we have the relation is KSP equal to S square for the AB type of salt. So the S will be equal to KSP raised to half. Then for the AB2 salt, the KSP will be equal to 4S cube. So S will be equal to KSP divided by 4 and the cube root. Then with AB3 salt, we have KSP equal to 27 S raised to 4. So S will be equal to KSP divided by 256 raised to 1 by 4. And for AB4 salt, we have the KSP equals to 256 S raised to 5. So S will be equal to KSP upon 256 divided by 1/5. If you observe, as you move with the salts changing from AB to AB2 to AB3 to AB4, and the number of ions in the salt increases. So first AB gives you only 2 ions, AB2 will give you 3 ions, AB3 4, AB4 5 ions. And if we look at the solubility, the KSP is raised to the 1/5 in the last case. And that's why the KSP will be having the highest, sorry, the KSP raised to 1/5 will have the highest value of S solubility. Of course, this will be S1, S2, S3, and S4. So the shortcut trick is if the salts have the same KSP, then more the ions, more is the solubility. The shortcut would be more the ions, more is the solubility. So this will be the detailed explanation, but the shortcut trick is more the ions, more is the solubility. And so we have to go with answer D. From the chemical kinetics, the rate constant of the reaction A to B is 0.6 into 10 raised to minus 3 mole per liter per second. If the initial concentration of A is 5 molar, and concentration of B, which is product, after 1200 seconds is. Now, thought process is the rate constant unit always gives you the order. So from the rate constant unit, we should understand that it's a zero order reaction, meaning the rate law will be rate equal to K times E raised to 0 equals to a constant K. So rate is always a constant irrespective of the concentration of A. So this concentration as such will not be affecting the rate of the reaction. Also, rate with respect to the reaction A to B is minus dA by dt and also equal to plus dB by dt. And that would be equal to K. So if I take this relation to get the B, then dB is the difference in the concentration of B. I can say Bt minus B naught upon T minus 0 equals to K. Now, B naught at the start would be 0, the concentration of the product. Therefore, the concentration of B after time t would be just equal to Kt. Okay, is given 0.6 into 10 raised to minus 3. And time is given as 1200. So this will be equal to 0.72 molar. That's the answer, option C. Methyl halides with the highest and least dipole moment values are. Now, the dipole moment values for the alkyl halides decreases in the order as chloride, chloride, bromide, and iodide. It is not in the order of fluoride, chloride, bromide, iodide. It's the exceptional order due to the large size of the chlorine, and that's why chloride has the highest dipole moment and iodide has the least. Answer will be option B. The normality of 1 molar solution of H3PO4 in the following reaction is. Now, this is a neutralization reaction. In case of neutralization, when acid reacts with the base, then the N factor is equal to the number of H plus and the OH minus neutralized in the reaction. So we know that H3PO4 is a tribasic acid having 3H plus, and it is reacted with the base consuming all the H plus ions. That's the reason 3H2O is formed. That's why the N factor will be equal to 3. And therefore, the normality will be equal to molarity times 3, and that's equal to 1 into 3, and that's 3 normal, option C. So the simple trick is number of H plus or the OH minus consumed in the reaction gives you the N factor. Through that, you can find out the normal. From the organic chemistry ether, the major organic product in the reaction given. Now, this is the reaction of ether with HI. Since the number of moles are not given, we have to consider this to be 1 mole, meaning cold HI reaction. Under cold HI, there were two cases. One, when both the alkyl groups are primary or secondary, it follows the SN2 mechanism with a simple trick that smaller one gives the iodide. Reason is the nucleophile will be able to attack the smaller species easily through the backside attack, and the larger one gives an alcohol. And case 2, if one of the group is forming a stable carbocation like a tertiary alkyl, primary allyl, primary benzyl, or any of the benzyl allyl group giving you a stable carbocation, in that case it gives SN, it follows SN1 mechanism with the stable carbocation forming the iodide, and the other one, whatever is left, will give you an alcohol. So this is an example of primary and secondary. So it will follow SN2. Smaller one would form iodide, other one would form alcohol. Hence, the answer is option C. The major product formed in the following reaction of third butyl bromide with sodium ethoxide. So this is an alkyl halide with the alkoxide. So reaction is basically the Williamson synthesis. Now, in Williamson synthesis, simply based on the halide, we have to understand whether it will undergo substitution or elimination. So the trick is alkyl halide, if it is primary or secondary, it will undergo substitution via SN2 to form an ether. Tertiary or the bulky alkyl group for the halide would undergo elimination by E2 mechanism. And in that case, the elimination will give you an alkene. Basically here SN2 and E2 compete with each other, wherein in this case, because of the bulky halide as a substrate, it will undergo elimination to form the famous alkene isobutylene. That's why answer is option C. The correct priorities in the decreasing order for the substituents shown below according to the EZ sequence rule. Now, EZ sequence rule is nothing but the atomic number rule, which we also use in the RS configuration. So what we do is for every group, we create a set. So CN is C triple bond N, which is considered as carbon attached to 3 nitrogen. So the set created is triple N. Second case may the carbon is attached to bromine and 2 methyl, which will have a set of Br and 2 carbon. Then the carboxylic acid is C double bond O OH. So the set will be double O with single O, meaning triple O set. The fourth set will be carbon connected to carbon and two hydrogen. So in the decreasing order of atomic number, CHH. For aldehyde, double O with a H. So now priority wise, the first atom with the highest atomic number in the set gets the highest priority. So 2 will get the highest priority. Then oxygen set, and in 3 and 5, the triple O set would get a higher priority than the double O wala group. And then comes the nitrogen, fourth one, and then this will be the fifth. So the answer will be 23514, option A. Which of the following shows isostructural species? Isostructural matlab having the same hybridization and the same geometry as well. So ammonium NH4 plus will have sp3 hybridization with a tetrahedral geometry. NH2 negative would have nitrogen with 3 bond pairs and 2 lone pairs. Hybridization is sp3, but it will be V-shaped or bent. Sulfur dioxide would be S double bond O with a lone pair. So it is sp2 with planar geometry, but the shape will be V or bent again. The sulfate is the conjugate base of sulfuric acid. In such case, you should know the structure of the oxy acid, sulfur with 2 OH and 2 double bond O. Remove the H and you get the sulfate ion as S double bond O, double bond O, O negative, O negative. Basically, now there are 4 PPs and no LPs. So this will be sp3 with a perfect geometry of tetrahedral. Phosphate will be PO4 minus 3, conjugate base of H3PO4. It will have P double bond O negative, O negative, O negative. Again, there are 4 BPs, no LP. It will have a perfect regular geometry of sp3 tetrahedral. BF4 negative will be having B with 4 fluorides, having the complete octet with a negative charge. So this will also have the sp3 hybridization with a perfect regular tetrahedral geometry. So these are having the same hybridization as well as the same structure, hence they will be considered to be isostructural. So answer is D. Rate of a chemical reaction increases with increase in temperature. Kinetically, the rate is proportional to rate constant, and rate constant as per Arrhenius is directly dependent on temperature. So this is a correct statement. Statement 2, on increasing temperature, activation energy decreases. Activation energy depends on the catalyst. Catalyst can increase or decrease the activation energy. Temperature as such would not have any effect on the activation energy. So this is an incorrect statement. So statement 1 is correct and 2 is incorrect. Option A. What will be EMF for the given cell? From electrochemistry, we have to apply Nernst equation. Before applying Nernst equation, you should always write the reaction. H2 will give you 2H plus and 2H plus would give you H2 gas. This is the H2 with the pressure P1 and this is the H2 formed with the pressure P2. Now, this is basically an electrochemical cell with the same type of electrodes. So the E naught of the cell is going to be equal to 0. And applying Nernst equation, we have to find the EMF, which will be equal to E naught minus 0.0592 can be taken as 0.06 by 2 into log of partial pressure of the products. So in this case, P2 upon partial pressure of the reactants P1. Now H plus concentration is not given, so we will consider them to be equal, and that is why it will get cancelled. So ideally it would have been P2 into H plus concentration square. Let's say this is C1 and this is C2. So C1 and C2 would be equal in that case, so it will get cancelled out. Now they have given this 0.06 in terms of RT. So it will be RT by 2F ln of P2 by P1 negative. Now the minus sign is not in the option, so we have to just reverse the log over here and it will be P1 by P2. Option B will be the answer. In which case, Vent-Off factor I remains unchanged. Okay, so Vent-Off factor is related to the number of particles. PtCl4 will have 5 particles, and with KCl, it forms K2 PtCl6, which will break down to give you 3 particles. So particles are changing. Zinc chloride with aqueous ammonia. Zinc chloride has 3 particles, and on reaction with ammonia, it forms a complex Zn NH3, 4, and Cl2, which is again having 3 particles. So the Vent-Off factor doesn't change in option B. Next one, if you observe, there are 4 particles in FeCl3 changing to 5. The KMnO4 reduced to MnO2. KMnO4 would break down to give you K plus MnO4 minus, so 2 particles, and MnO2 in alkaline medium. This is actually a covalent compound, doesn't break down. So can't apply the Vent-Off factor. So you have to anyways consider this to be 1 particle. So 2 to 1, it is changing. When dihydroxyacetone reacts with HiO4, the product is R. Now this is related to the cleavage of CC bond of the glycol or the carbonyl on reaction with HiO4. So if you talk about glucose, then glucose has an aldehyde at the start. Then there are CHOH repeated 4 times, ending with a primary alcoholic group, CH2OH. So HiO4 has a tendency to cleave the CC bond of carbonyl and OH or between the glycolic CC bonds. So 5 moles of HiO4 will be consumed. The shortcut trick to find the products of HiO4 reaction is, if you have an aldehyde, then it will change into formic acid. If you have a primary alcohol group, it will change into formaldehyde. If you have a secondary alcoholic group, it will oxidize into formic acid, and a carbonyl group, keto group, will change into CO2. So with this trick, you can understand that the formaldehyde will give you, so the aldehyde group will give you formic acid. Even all 4 secondary alcoholic group will give formic acid. So there will be 5 moles of formic acid and primary alcohol changing to formaldehyde. This is how you identify the products. Now we are given dihydroxyacetone, which is the simplest ketose, optically inactive. The structure is CH2OH, C double bond O, and CH2OH. So this is the bond which is going to break down. Again, this. So it's going to utilize 2 HiO4, and the first and the last would give you formaldehyde, so 2 moles. The carbonyl will give CO2. Answer would be option